you guys. So what we're going to start looking at is kind of what we were talking about yesterday. Let's look at this sequence. So if I have the sequence 1, 1/2, 1/3, 1/4, 1/5, and so on. So yesterday we were saying, okay, that is a sequence. There are a couple different ways to denote that sequence. So I wanted to go over a couple of those now. One is to just make the list of numbers where there's a clear pattern as far as what is going on in the sequence. So I think it's pretty clear from that that the next term would be 1/6, then 1/7, then 1/8, and so on. We could also write this way. We could write it this way. If we define it the way that I've written it here on the second line, then this is A1, this is A2, this is A3. So it's the first term, second term, third term. If we define it this way, then this one's A3, this one's A4, this one's A5, then there is no A2, the way that we're defining this. You could also define it the way we said yesterday as like 1 over, say, n plus 5 for n greater than or equal to -4. So this term then would be a -4. So there's a -4th term, there's a -3rd term, there's a -2nd term, which is a little bit weird. The first term is later on. There is no -5th term. So what we said yesterday is that we're going to define a sequence as a function whose domain is the set of integers greater than or equal to something. And so we can write these this way. I want you to see another notation because you'll see this sum in the homework. I'll use this sum. You may see this on a test. So you can also write this with braces. So you could say that. And then a lot of times what we'll do is put like n equals 1 to infinity there. So this notation is exactly the same as saying this. This notation on the second one, we can write 1 over n minus 2 for n equals 3, 3 to infinity. And then we could say this one is 1 over n plus 5 for n equals -4 to infinity. And so all three of these are the same as these three. They're different ways to label the same sequence, the same list of numbers. And so we want to be comfortable with all those. There is always a first value in the sequence. So maybe it's for n equals 1, or maybe it's for n equals 3, or maybe it's n equals 0. The most common are for n equals 1 or n equals 0, but it could be whatever we want, the way we're defining sequences. So it's the domain is the set of integers greater than or equal to some integer. Now, yesterday we did repeatedly say, okay, the domain is all integers. So if the domain is all integers, how come we're allowed to have 1/4? So domain is numbers where there's nothing after the decimal point, but 1/4 would be 0.25. So how come this is not against the definition of a sequence? What do you guys think? You could say it out loud or put it in chat. Got both of those ready to go. So like this first one, why does this meet the definition we gave yesterday, even though 1/4 is there?
Because the domain is the input and 1/4 is the output.
Yeah, so the domain is the input. And in this case, that's the values of n. The range is what we would think of as a function as being the output. And so 1/4 is part of the range, not the domain. So there is no restriction on what the sequence values can be. There is a restriction on what the subscripts can be, or what the inputs or domain values are. So these have to be integers. The answers, the corresponding sequence values, do not have to be integers. Okay, at the beginning and most of the time, what we're going to be dealing with in calculus is the limit of a sequence. And we said yesterday there's only one limit that we could potentially be talking about. And the limit as n does something. What limit is it that we could be talking about when we're talking about a sequence? Limit as n approaches what?
Infinity.
Infinity. So when we talk about the limit of a sequence, so the limit of a sequence that's understood to be the limit as n approaches infinity. So we understand when we talk about the limit of a sequence that it's the limit as n goes to infinity. That doesn't mean the limit itself has to be infinity. That means we're always talking about the limit as the subscript approaches infinity. So in this case, what do you think the limit of this sequence is as n goes to infinity? No matter which of these forms we use, or if you just look at this list of numbers, fairly clear that that sequence does what?
This is 0.
Yeah, the limit of that sequence is 0. So we have several notations that mean the same thing because of this. So the notation's a little bit looser than it is in Calc 1. So when you do limits before now in calculus, everybody should have been in your intro calc class very strict about writing limit notation every single time and writing that limit as n approaches infinity each time when you're doing work on a sequence or on a function. That should be the case. On a sequence, we can be a little bit looser because we understand that the limit of the sequence is always as n goes to infinity. So if you want to use shorthand, we're going to allow us to use shorthand like this. We're going to be able to say, okay, an approaches 0, and writing that means this because we understand the limit that we're talking about is the limit as n goes to infinity. So without writing this part, we understand this. So both of those are interchangeable. You can use this notation and you can use this notation to mean the same thing. That is saying the limit of an as n approaches infinity is 0. That's both of these. So both of those statements mean exactly that. They mean the limit of an as n approaches infinity is 0. You can also write an converges to 0. And that means exactly that same sentence. So this sentence, the limit of an as n approaches infinity is 0. All three of those statements mean exactly the same thing. We can also write the limit using this first representation. We can write the limit as n approaches infinity of 1 over n equals 0. That means the same thing when an is 1 over n. And you can write 1 over n goes to 0. That means the same thing. So if you took Calc 1, notation should have been very strict and not allowed something like this. It is allowed here because it's understood as n goes to infinity, but it would be wrong to write this. So if you wrote that an equals 0, that's not true, right? So if you want to use an equal sign, then you need to use limit notation. The limit is equal to 0, but an is not equal to 0. If an were equal to 0, all of the terms would be 0, which is not what we're saying. Does that make sense to everybody? So it's wrong to write that this is the case. It's also wrong to write this. It's wrong to write the limit as n approaches infinity of an and then arrow 0. So we don't write it that way, not necessarily because that'd be bad. It's just not standard to do that. This limit, and I guess kind of is bad, this limit as n goes to infinity of an, that's normally going to be a number. So it's not that this number approaches 0, it's that this number is 0. So when we use this notation, we should use an equal sign. So if you want to use the limit notation, then you should use an equal sign. If you don't want to use the limit notation, then you need to use an arrow. Does that make sense to everybody? All right, so the notation is specific. It's not quite as exact as it is when we're dealing with limits in general. The reason for that is because when we're dealing with limits in Calc 1 and limits in general, x or n may not be approaching infinity. In these problems, n is always going to be approaching infinity when we're talking about limits. Another comment is that that means that in a lot of problems, we're just going to deal with this or this, where we don't specify the first value. And the reason we can do that in a lot of cases, so we don't say, hey, it starts at 1 or it starts at 3. A lot of times we won't specify that when we're talking about limits, because for the limit, the beginning doesn't matter. So it doesn't matter if you want to start this at 1 or 2 or 3. Like if we had the sequence where we eliminated these first two terms, if we just said, okay, 1/3, 1/4, 1/5, so maybe this one starts at n equals 3, then the limit is still the same. So the starting point does not matter for the limit as n approaches infinity. So a lot of times we'll gloss over where the sequence starts because a lot of times what we're going to be talking about is the limit, and so we don't care about the first several values. Does that make sense to everybody? Clear? If we're in a situation where we do care about the first several values, or we're trying to find a formula, then okay, we need to worry about where does it start. So is it n greater than 1 or is it n greater than 0? That's important in some situations. It's not important in a limit situation. So if we're trying to find the limit of a sequence, which is the big first big thing we do, if we're trying to find the limit, it doesn't matter where it starts. Okay? Any questions so far? So we made a big deal yesterday about making sure we understand every little thing. This isn't exactly a summary. I'm just trying to clear up a few things about notation and what the ideas that we were talking about yesterday were. The idea yesterday was just kind of explore what's going on, see what a sequence is, see what a series is. We're not going to talk much about series again until next week, but you were looking at examples of series. We were looking at those in yesterday's lecture, and then on the take-home quiz, you're also looking at series. But for the sequences, this is kind of somewhat a summary, but also an idea of the notation and just these 5 things all meaning what I've got circled here. Any questions at all? Can be anything related to this. Everybody good? Okay. All right, so I'm going to take that as a we are good. Okay, so then the next thing we're going to do a bunch of problems where the directions for the problem say, let's see, we're going to say show whether the sequence converges or diverges. And then if it converges, find its limit. Okay, and so we're going to do a bunch of examples like that, and we're going to come back and fill this in. But I want to talk about a quick review of some ideas in Calc 1, and we're going to kind of keep doing this. We're going to review a little bit and then come back and do another problem. If you have something like this, if I have like 2 divided by that, what is that?
Almost 0.
Almost 0. So that's like point a bunch of zeros and a 2. Does that make sense to everybody? Okay, that's point a bunch of zeros and a 2. If I do this, It's point a bunch more zeros and a 2. The idea is, what if it's negative 2 divided by that? Then it's negative point a bunch of zeros and a 2, and it's still basically 0. Does everybody see what I mean? And then what if it's negative divided by negative? Is that's now positive a bunch of zeros and a 2. And what if it's positive divided by negative? Now it's negative a bunch of zeros at point a bunch of zeros and a 2. So that's basically 0. That's getting informally at the idea that if you have a constant divided by plus or minus infinity, what does that do?
Goes to 0.
It goes to 0. So that's an idea from Calc 1. Nothing I'm writing here is formally correct, but that's the way we think of it. If we have a constant number divided by infinity or negative infinity, that goes to 0. What if I flip it? So what if instead of 2 over whatever that ridiculous number is, instead of 2 over that, I have that over 2. So instead of 1 with a bunch of zeros after it, now I have 50 with a 1 less 0 after it, but you have 5 with a bunch of zeros after it. It's still huge, it's just not as big. Does that make sense to everybody? So then, okay, that's infinity if we add more and more zeros. So if I have infinity, either infinity or negative infinity over a constant, that goes to either infinity or negative infinity, depending on how the signs work out. Does that make sense to everybody? Everybody clear? Again, informal to think about that. Maybe weird to think about if the constant's 0. We might have to do a little more examination. Turns out we need to think about it a little bit more, but it goes to infinity or negative infinity as well. But infinity or negative infinity over a constant, depending on how the signs work out, that limit goes to infinity or negative infinity. If these are both positive, obviously it's positive. If this is negative down here, positive there, negative infinity. If they're both negative, then it's positive. And then if it's negative over positive, it's negative. And so either way, though, it approaches infinity. And that's a good way to think about that. It's not the only way to think about that, but it's one way to think about that. And so we're going to accept these things as fact, that if we know it's approaching a constant over infinity, we know that's going to 0. We're going to know that if it approaches infinity over a constant, we know that's going to infinity or negative infinity. We're going to accept that as fact. We know that already. We're also going to, I want to say one thing about the word converge and diverge. So when we say it converges, so if we say a sequence converges, we're saying the limit exists, that the limit is a number, not plus or minus infinity. Okay, so the limit is a number. It could be 0. A lot of times it is. Doesn't have to be 0, but it approaches some number. It does not approach infinity. It does not approach negative infinity. And it doesn't just not exist. So it doesn't like bounce between 1 and -1 like we were doing on 1 yesterday. If we say it diverges, the limit doesn't exist. So we're saying the limit does not exist. This includes plus or minus infinity as possibilities. Okay, so it's a possibility that if it diverges, it goes to infinity or negative infinity. So if we get one that goes to infinity, diverges. If we get one that goes to negative infinity, diverges. So we're going to come back and do more of this, but I want to look at a couple of examples of how we show something like that. So if I have, for instance, an equals 1 over n, which is the first sequence we were talking about at the beginning, then okay, as n approaches infinity, it's clear that the top does what? And the bottom does what? What does the bottom do as n gets really, really big? Easy question. What do you guys think? The bottom is n. So if n gets really, really big, the bottom also gets really, really big. It goes, yeah, it gets bigger. And so but the top is a constant. And so we accept this fact, okay, that's a constant over infinity. And I'll write my work in blue, my bad. So black is what the problem is. And so when I do the work, I'm going to write, okay, 1 over n goes to 0. We're going to accept that as fact because we've got a constant over infinity. You can write it that way, or you could write this of 1 over n, or you could write an, either way. And now you've answered the question. So you have shown whether the sequence converges or diverges. What did you just show? Does it converge or does it diverge?
Converges.
It converges because you got a number for the answer. And the number doesn't have to be 0. It just happened to be. And then it says if it converges, which it does, find its limit. Well, we did. The limit's 0. So you're saying that you can write it this way, or you can write it this way, whichever you prefer. There's no need to do both. You can do the one you like better. I will go back and forth. I'll typically do this, but sometimes we'll use this, especially in more complicated problems. Does that make sense? All right. So then the next one, we'll make it pretty easy. Let's say we have n to the third over 6. So if I have n to the third over 6, then, okay, what happens as n goes to infinity? As n gets huge, what does n to the third do? So if n gets infinitely large, what does n to the third do?
It's even more infinitely large.
Yeah, it gets infinitely large even faster. And then what happens to 6 as n gets infinitely large?
Stays constant.
It stays as 6. So we have infinity over 6. That's going to go to infinity. So we have n to the third over 6 goes to infinity. That's a very simple example. We know that's infinity over 6, so that's good enough. Now, did we just show that that converged or diverged?
Diverge.
It diverged because we did not get a number. So then when that happens, we need to explicitly say that the sequence diverges. So technically the answer to this, if you're thinking about it as a problem that then has an answer, the answer is that the sequence diverges. The reason why is because it approaches infinity. But when a limit is infinity, the limit technically does not exist. The limit only exists if the limit is a number. Does that make sense? Infinity is not a number. Good? Okay, so I want to look at a couple other simple examples. So back up here, questions so far? You guys good? My fault. Not a committee. All right. So back up here, if we have a constant over infinity or infinity over constant, we know what happens. What if we have something like this? So what if I've got, and we'll do these just to separate it in purple. So this stuff that I'm writing on this screen is just kind of a thought process, not anything formal for sure. But if I have like 2 to the 50, I don't know, billion, trillion, quadrillion, whatever this is. So if I have that, what is that? 2 times 2 times 2 times 2 is already 16, times 2 is 32, and then 64, and then 128, 256, 512, 1024, 20, man, something else, 2048, so on. What happens as you multiply by 2 a bunch?
Gets closer to infinity.
It gets huge. Yeah, it goes to infinity and really fast. So like by the time you're at like 2 to the 10th, you're already in like 4 digits, I think. And so this gets huge, really, really, really quickly. And so this goes to infinity. So if I have 2 to the infinity, that approaches infinity. Again, informal to write that, but we can think of it that way. Would 3 to the infinity do the same thing? Yeah, even faster. So 3 times 3 times 3 times 3 goes to infinity even faster. The problem is, what does this do?
Goes to 0.
that goes to 0. Could somebody explain why? And it could be you.
It's because that kind of squares. I mean, you can look at it as it's squaring the denominator as well, so that denominator is getting larger and larger. But
The denominator's getting larger and larger, and actually that's the only one that's getting larger and larger. Does that make sense? Like 1 to whatever is 1. And so the bottom gets huge and the top stays. And so that's 1 over infinity, which is 0. Does that make sense, everybody? Okay, so then 1/2 to the infinity goes to 0. What do you guys think happens if I have 1/5 to the infinity? What's that going to do? That's going to go to 0 as well, because it's going to be 1 over infinity. What happens if I have 5 over 4 to the infinity and 4 over 5 to the infinity? These are two different answers. What do you guys think?
The first to infinity and the second to 0.
Yeah, the first one goes to infinity. The second one goes to 0. The reason that is because this is really 1.25 to the infinity. When you do 1.25 times 1.25, that gets bigger. And then when you do times 1.25 again, that continues to get bigger. When you multiply by 0.8, 0.8 times 0.8 is 0.64. And then 0.8 times that is 0.512. Those numbers get smaller. And so the breaking point, when do they go to infinity and when do they not? When do they go to 0 when you're talking about stuff like this? What do you guys think?
It goes to infinity if it's bigger than 1.
It goes to infinity if the base is bigger than 1, and it goes to 0 if the base is between 0 and 1. Does that make sense to everybody? And so if you have a to the infinity, that depends. So that goes to infinity if a is bigger than 1. If you have a to the infinity, that goes to 0 if a is between 0 and 1. And so that's a big deal. So like 4/5 less than 1, that goes to 0. So that 4/5 to the infinity. 5/4 bigger than 1, and so that goes to infinity because again bigger than 1. If you have 1, what happens? So what if I have 1 to the infinity?
Just going to go to 1.
It's just going to go to 1, probably. There's something about 1 to the infinity that you learn in Calc 1. It has a name. Anyone remember?
Is that an indeterminate?
It's an indeterminate form. So like, remember infinity over infinity and 0 over 0 and 1 to the infinity, and then there's some others as well. 0 to the 0, infinity minus infinity, some other ones like that are indeterminate forms. What is an indeterminate form? Does anyone remember? Like other than it's those? Indeterminate form sounds really complicated, but what does indeterminate mean? So it's a form where we don't know what happens. And so like if the form is a number to the infinity, we do know what happens if the base is bigger than 1 or if the base is between 0 and 1. If the form is 1 to the infinity, we do not know what happens because it's in the indeterminate form. But why does that make any sense? Like 1 times 1 is 1. And then if you multiply by 1 again, I think that's still 1. And if I multiply by 1 again, it's still 1. And if I do it a billion times, it's still 1. So then why would this be indeterminate? That's something you learn in Calc 1. Why is 1 to the infinity? Why is that form indeterminate? What does it mean to say the form is indeterminate? Okay, so we're going to get to that. But the idea here is that you have a number where you know that the form, if you have 2 to the infinity, it goes to infinity. But if something approaches 2 to the infinity, it also goes to infinity. If it's 1 to the infinity, if it is the number 1, so if I look at the expression 1 to the n as a sequence, that goes to 1. There's no question there. That is not indeterminate. That 1 to the n goes to 1. But you might remember from Calc 1 that if you had an expression like this, where I have like 5n minus 7 over 5n plus 3 to the n, that if you ignore that n, this inside goes to 1. Does everybody see that? We're going to review that in just a minute, but 5n over 5n goes to 1. And so this approaches 1 to the infinity, and then it's not actually 1. And so that's when we don't know, where the form is 1 to the infinity, but this fraction in there is not actually 1, it just approaches 1. And so that is when it's indeterminate and it's harder, and we don't know necessarily what happens. Does that make sense? Okay. So now let's think through some more problems. Any questions so far? Again, remember we keep saying how this is going to build, so it's real important we understand every little detail. We will talk more about the indeterminate form later, but it should make sense, this part that I've got in red. So these two are real important, that you know those, but we also understand why they make sense. Everybody good? All right. All right, so number 3. Okay, so if I have 4 to the 5n plus 6, as n approaches infinity, what happens to 5n? So like if n becomes a million and then a billion and then a trillion and then something way bigger than that, what happens to 5 times it?
Goes to infinity.
It goes to infinity. And then if I add 6, it goes to infinity a little bit quicker. And so then, okay, this exponent gets infinitely large. Remember, we're looking at the limit as n goes to infinity. So as n goes to infinity, this exponent goes to infinity. So if I raise 4 to that, then what happens? If I raise 4 to the infinity, what does it do?
It goes to infinity.
It goes to infinity. So then we're going to accept that as fact because it's clear. This approaches 4 to the infinity. That means that the whole thing approaches infinity, so this diverges. Okay, so then number 4 is if I have an equals 1 over 6 to the, let's do it this way, 1 over 6 to the n minus 8. So as n goes to infinity, what happens to n minus 8?
Goes to infinity.
It goes to infinity. So then what happens when we take 1/6 to the infinity? That goes to 0, and so this
0.
converges to 0. Does that make sense to everybody? You guys good? Okay. Now, what happens if I do this? What if I've got an equals 6 to the negative 3n? So if I have 6, again, we're back up here. Show whether it converges or diverges. If it converges, find its limit. That means we're trying to figure out limit as n goes to infinity. So, okay, as n goes to infinity, what happens to negative 3n?
Goes to 0.
The whole thing goes to 0. Negative 3n goes to negative infinity. So, like, what you can think is, okay, that means we've got like 6 to the negative 300 billion or something weird like that, or something, whatever this is. So negative 300 whatever. And so what does that negative exponent do to the 6? It
6 over that.
Yeah, it makes it 1 over that. So we get 1 over 6 to whatever. And so this is, however many zeros. And so this is 1 over infinity, which means this goes to 0. So you could write it a couple ways. You could just go ahead and say that goes to 0. Or if you wanted to, you could say, okay, that's the same thing as 1 over 6 to the 3n. Well, then that's 1 over infinity, which is 0. on this one, it would be okay if you did not have that middle step, if you understood this goes to negative infinity. So 6 to the negative infinity is 0. That's fair. Or if you want to flip it to show a little bit more, that's fine too, where you get 1 over infinity. Either way, this statement is saying that it converges to 0. Does that make sense? Okay, a quick addendum we can make up here is that if we have a to the infinity, that goes to infinity. If we have, a to the infinity where a is bigger than 1, that goes to infinity. A to the infinity if a is between 0 and 1, that goes to 0. But then we could add on to that, that equivalently, a to the negative infinity goes to 0 if a is bigger than 1. And then a to the negative infinity goes to infinity. Man, that's an error. If a is between 0 and 1. Okay, so it flips because it flips the fraction, basically. That makes sense? Okay. We are going to do more problems like that, but I want to talk about this for a second. So if you're writing, stop writing for a minute, and I just want you to look at the screen and think about this. And what I'd actually like you to do is send in the chat, and if you don't want to send it to everybody, you can send it just to me, or send it to everybody. You're allowed to be wrong. But I want to know, without a calculator, without any writing, what is the answer to this problem? Okay. So send in the chat what that is. No calculators, no writing. What's the answer if you simplify that? Yeah, everybody's right so far. Those are tildes, not negative signs, I think, right? Okay. It's positive, but it is 16,000. And so it's not exactly 16,000, right? But it's pretty much 16,000. Why? Because it's the top is pretty much 32,000, right? In comparison to 32,000, this is nothing. And this, I don't even know how to read that number. That's nothing. And same here, this bottom, it's 2. 2 minus this is 1.99999, whatever. And then 1 over that is 0.0 whatever. The bottom is basically 2. So this is basically 16,000. Probably most calculators, if you type this in, would give up and just give it 2. It'd lose the decimals. I don't know if that's true, but it'd be pretty much 2. Does everybody see why? Everybody get that? Okay. So this is pretty much 32,000 over 2, which is 16,000. So when we do the next problem, number 6, if I do this and I say, okay, I've got 8n to the third minus 456,000 n squared plus 125 over, let's do 2n squared plus 4n to the third plus 265 n minus 1. All of a sudden, that looks a lot harder. We're back to the original instructions. Show whether this converges or diverges. If it converges, find its limit. how can we use this idea that the top is pretty much 32,000, the bottom is pretty much 2, to figure this out? So there's an obnoxious comparison between 32,000 and this ridiculously small decimal. So everybody see that? Okay, is a very clear comparison between that. This is so much bigger than this that this doesn't really matter, right? In the approximation of the answer, this doesn't really matter much. Same deal here. 2 is so much bigger than this doesn't matter. 2 is so much bigger than this doesn't matter. We're looking at this as n does what? As n approaches what?
2?
The answer to this is 2, but we're looking at this as n goes to infinity. So I can say in my work that this approaches 8n to the third over 4n to the third. The reason I can do that is because, okay, I'm not looking at you guys because we're on Zoom, but if you're not looking at the screen, look at the screen for a second, okay? So look at the screen and say, down here, we knew 32,000 so much bigger than these two didn't matter. 2 so much bigger than those, they didn't matter. Same deal here. N squared gets really, really big, right? So it's not as obvious. But when you're talking about n approaching infinity, infinity is like, if you think about 100 billion to the third, you have 100 billion times 100 billion times 100 billion versus only 2 of them here. And 100 billion is tiny. You could have 100 billion with another 100 billion zeros after it, and you've got 3 of them here. Here you only have 2 of them, which means this comparison is more ridiculous than this one is. Does that make sense? Like 32,000 is clearly so much bigger than this. It's obviously 32,000 on the top. Here, 8n to the third is even more of a ridiculous comparison to this one than it is down here. 8n to the third is infinitely larger than n squared. And 456,000 is laughably small. Does that make sense? That is weird to think about, but does everybody understand that idea? Okay, as n goes to infinity, that's why we're writing an arrow. In no way is this equal to this. The limit of this is the same as this. Same on bottom. 4n to the third is infinitely larger than any of the other 3 terms on the bottom. So as n goes to infinity, the only thing that matters on the bottom is 4n to the third. That means that if it approaches this, as n gets really, really big, it approaches this, but that's 2. And because the n cubes cancel. So then, okay, this converges to 2 and we're done. Does that make sense? So, okay, in the chat, so pick the bigger number on top and bottom to simplify it. Yes, and we will accept that when it's obvious. And obvious is a loose word, but when it's a power function versus a power function, meaning I have n to the third versus n squared versus n to the 0, then it's very clear that this one's bigger. That's when it's okay to do this. Does that make sense? That's a really good question, Gabrielle. Does that answer the question? Does that make sense to everybody? Okay. Okay, cool. Now, in Calc 1, you learn techniques, and the book will show you techniques where you can go through and multiply by 1 over n cubed. You're welcome to show that if you want. I would rather you think of it this way, but you can only make these comparisons when it's really obvious. It's not as obvious. Like, it's obvious n to the third is bigger than n squared. It's not as obvious as whether n squared is bigger than like natural log, or whether n squared is bigger than 2 to the n. Turns out maybe it is obvious, but we haven't said that yet. When it's the same type of functions, then it's obvious. Because that's what we will consider to be obvious. Other questions so far? Okay, so then number 7, I'd like you guys to try this one. I'm going to give you about 30 seconds to work on this, and then we're going to check it together in a second. Okay, so on this problem, we have functions that are all the same type. You've got n squared versus n to the first. You've got n versus n squared versus n to the third. All of them are the same types of functions. So we pick the biggest on top, biggest on bottom. The biggest on top is 8n squared, which is weird because this number is really big. But when you talk about n going to infinity, this number is tiny. You could have this number with that many more zeros after it, and this doesn't change, but n squared does. Does that make sense? And then on the bottom, the biggest term by far is n to the third. And when we're using the word biggest, I'm glad if you look in chat, she put it in quotes, that's true. Biggest is a loose term. We're talking about absolute value being the biggest. So the negative carries with this. It does not affect this answer, but could affect others. And so the negative carries with it, but n to the third, the absolute value of that is bigger than n squared, even though technically the negative is smaller. All right, is that what we picked? Cannot see anybody's face, so everybody, we're getting that, I assume? All right, and so then that simplifies to negative 8 over n. The negative can go wherever you want there. It can go on top or bottom or outside, but now that's a constant over infinity, which goes to 0. So this one converges to 0 based on the same logic as before. Does that make sense to everybody? Any questions? Okay, number 8. There's a question in this chat. Would it be fine to skip the middle step on 7? Like, as far as would I take points off if you skip it? No, I won't take points off. I would try not to, because this stuff will get more complicated. So like picking out the biggest term and just kind of getting that solidified, I think helps you. If it doesn't help you and I'm wrong, then don't do it. But when it gets harder, I think it will help you to do it. Does that answer the question? Yeah, I understand what you mean, Evan. Like skipping to negative 8 over n. Like I'm fine with that. It's just I think it helps to do this, especially when it starts to get harder. Okay, so I would recommend not skipping it, but I'm not going to make you write it. Okay. All right. Other questions so far? All right. So what should I do on this one? I'm going to let you guys tell me this time. You can tell me in chat, or somebody can unmute yourself. So I should pick biggest thing on top, biggest thing on bottom. What's the biggest thing on top?
5n squared.
5n squared. And what's the biggest thing on bottom?
6n.
6n.
6n. And now that simplifies to what when I do the algebra? 5n. Perfect. And then what happens to that as n goes to infinity?
Goes to infinity.
That goes to infinity. So we just proved that this sequence diverges. Does that make sense to everybody? Any questions so far? Why not just 5 over 6n? Good question. Oh, you mean, oh man, it should be that. Sorry. But that still goes to infinity. My bad. Is that what you're saying, Gabrielle? N should be on top for sure. But 100%, I just dropped the 6. Everybody good? Questions? All right. Either way diverges on that. Okay. Let's go to this one, number 9. Let's make it 16n to the 8th plus 2n minus 1 over. Let's make it So if we look at this one, I just want to look quickly at how we deal with radicals. It's the same stuff. Radicals just make the exponents fractional. And algebraically, you cannot take the square root of each part. We talked about that a good bit when we were starting into trig sub. So it's not like you can split this up. But in terms of thinking about the largest term, you can think of them independently when you think of what the biggest term is. So on the top, the terms to consider are n to the third, the square root of n to the eighth, the square root of n, and then the square root of n to the 0. And so the biggest within the square root is n to the eighth. The square root of that is n to the 4, because you divide the power by 2 when you take the square root. So n to the third versus n to the 4, we're going to pick the n to the 4. So when you pick that and take the largest term, we're going to say, okay, that approaches the negative square root of 16 n to the eighth. The coefficient in front of the square root matters. So the negative 1 carries down. The coefficient with the n to the eighth matters. Is everybody clear why we pick square root of n to the eighth over n to the third? Okay, on the bottom, we've got n to the fourth outside. On the inside, the biggest one is 8 n to the 9. But what is the cube root of n to the 9? N to the third. Yeah, so because you divide by 3. So we're looking at n to the 4 versus n to the third. So we're going to take 5 n to the 4 from the outside. Does that make sense? Everybody clear? Okay, now we're going to simplify that, and the square root of 16 n to the eighth is 4 n to the fourth over 5 n to the fourth, and so this sequence converges to negative 4/5. So the two parts of the question show whether it converges or diverges. Well, it converges. If it converges, find its limit. Its limit is negative 4/5. Questions? You guys good? Okay. All right, you know what? My bad. We're still calling this number 10. All right, so if I have this, I want to show some weird algebra with exponentials. So the exponentials we know how to deal with are ones like this, where you have a number to the n, and the power can be relatively complicated, it doesn't matter much. But if I have like 1/6 or 4 to the n, if you have an exponential over an exponential, it's not as clear. And so what we want to do is we want to do some algebra to get it into that. And I'm going to show a little more than I normally would here. I'm going to use arrows, although for these first couple steps, we could use equals. And again, I might skip this step a lot, but is everybody clear why that step's allowed? So the idea is that if you multiply two exponentials with the same base, you then add the exponent. And so 3 to the 7 times 3 to the n is 3 to the n plus 7. So I'm allowed to split it up like that. Same thing down here. 2 to the 5 times 2 to the 2n is 2 to the 2n plus 5. So again, I'm allowed to split it up like that. The reason that's a good idea is because 2 to the 2n is the same thing as 2 squared to the n, because a power raised to a power, you multiply the exponents when that happens. And so we can rewrite this as 3/7 over 2 to the 5th times 3/4 to the n. Does everybody see where I'm getting that? Please ask it. If the question is, no, I do not see, I can try to explain it again. Everybody good? Okay, so how does that help me get the limit of this? So as n goes to infinity, what happens to 3/4 to the n?
Goes to 0.
That goes to 0 because 3/4 is less than 1. What happens to this part? So that doesn't change, but you have this ridiculous constant times 0. Well, then that's 0. So this converges to 0. Does that make sense? Okay. So then if I have this, then normally what I'm going to do is jump from here to this step. So take a minute and see if you can figure out how I got to that step. And then if you have a question, let me know. Okay, so just kind of as a heads up, I'm splitting it like this. So 2 to the -1 times 2 to the 5n. But then 2 to the 5n is like 2 to the 5th to the n, and that's 32. And same deal here, it's 3 squared and then 27 to the n because 3 to the 3rd is 27. And now 32 over 27 is bigger than 1. So we have a positive constant times infinity. That goes to infinity, which means this diverges.
Would the numbers ever get like big enough where we couldn't do this method?
What do you mean big enough where you can
Like,
do the method?
If that coefficient on like the 2 to the 5th n minus 1, what if that was like, I don't know, 27 n minus 1? Like,
Yeah.
we wouldn't really be able to calculate all that out. So is there?
Could though. So like, no matter how big this is, it's not going to matter in comparison to the one that's raised to the n. Do you get what I'm saying? Or maybe
No,
I don't.
I'm saying like the 2 to the 5th n minus 1, if that was like not 5n but rather 27n.
Yeah, okay. So then, okay, you can do this. You know, and just so there's no confusion, let's make this 28. It doesn't matter that the 27 is a match, right?
Uh-huh.
And so, okay, you're just saying, okay, you can't compute to the 28th without a calculator, right?
Yeah.
Okay, but you probably understand that 2 to the 28th is bigger than 27. And so, yeah, like, perfectly good question. Not trying to say anything bad about it. Like, you don't have to figure out that it's 32 as long as you can tell which one's bigger. So, okay, that goes to infinity.
Yeah, I'm just wondering if there's ever going to be a case where it's like we can't really determine, like.
No, I won't give you any problems where you can't determine which one's bigger.
Okay.
Unless they're the same. You know what I mean?
Yeah.
Yeah, but you should be able to determine which one's bigger. Okay. All right. Good question. Other questions? Okay. All right. So then number 12 is going to be this. So if I have an equals 3 to the 4n minus 1 plus 2 to the n plus 6 minus 12 to the n minus 7 over 3n plus 5 plus 9 to the 2n plus 1 minus 2 to the 3 minus 6n. Okay. So we said, I'll give you a second to write that down if you're taking notes. But now, if you aren't done writing it, write it in a minute, because I would like you to look at this when we're talking about it for a second, because it's a lot to talk about. We said you can take the biggest thing over the biggest thing when it's obvious which is bigger. And so when they're all power functions, we will consider that obvious. So if you have n to a constant, it's clear which one's bigger. It's clear that n to the 3 is smaller than n to the 4, and that n to the 4 is bigger than n to the 3. When it's exponentials, we will say, okay, it's clear when they're both exponentials, which is bigger. But when we're comparing them, because of the way this algebra works, I'm going to think of this first one as 81 to the n. Is everybody clear where I would get 81 to the n? So because I'm going to be doing this, where I have, instead of like 2 squared to the n, it's going to be 3 to the 4th to the n. So this is 3 to the 4th, so 81 to the n, versus 2 to the n, versus 12 to the n. So then when I pick the biggest one, I'm going to pick, whoops, we'll do it blue again. I'm going to pick 3 to the 4n minus 1. And then on bottom, I'm going to compare this one as 27 to the n, because it's 3 to the 3rd, versus this one as 81 to the n, because it's 9 squared, versus this one as 2 to the negative 6. That's 1 over 64. So we're thinking, and I'll write it in red, we think of this as 27 to the n, 81 to the n, and 1 over 64 to the n. And so we pick 81 to the n, which means we pick 9 to the 2n plus 1. Questions on that? Everybody good? Okay, it's important that the negative exponent normally would flip to the top if it were not being added to these others. So if it was just this in the bottom, the negative exponent would algebraically move that to the top, which would affect what's going on in the numerator. Here, it's overpowered by these very, very quickly, so it doesn't matter. These are so much bigger, it doesn't matter. And you can kind of think back to this original problem where if I had that 1 over whatever, this, because it's being added to these, does not get flipped to the top. But if it was just this on the bottom, it would. Does that make sense? Okay, so once I'm here, now it's like numbers 10 and 11. I say, okay, well, that then approaches 3 to the negative 1 over 9 to the 1st times 81 over 81 to the n. That is 1 to the infinity, but it's not just the form 1 to the infinity. This is actually the number 1. So when that happens, when it's actually the number 1, it's not indeterminate. This goes to 1. So this approaches 3 to the negative 1 over 9 to the 1st. That simplifies to 1 over 3 times 9. And so this converges to 1 over 27. Questions? Okay, so I want to talk about what I need you guys to do as far as homework to stay on top. So you're going to have for this week, you have the take-home quiz that's due tonight. That's based on yesterday's. Okay, so you have that's based on Monday lecture. And then you're going to have 2 web assigns. One of them is up. One of them will be up tomorrow or Thursday, probably tomorrow. Sequence limits 1. And probably we're just going to call this one sequences 2. It's not just limits. So sequences 2, whatever. Those are the 2 web assigns. Those will be due Monday like normal. But you really need to do the worksheets in the shared drive. And so like tonight, I'm not collecting this, so it's your call. But you need to do this one, and I'm going to share it on the screen so we can see it. This is the sequences 1 worksheet with solutions. It's now in the Unit 3 folder 1. This has a ton of sequence proofs, and then it has worked out answers. There is a mistake somewhere on number 10, I think, where I copied 2 different problems. When somebody finds that, let me know, and I'll try to post a corrected version. But these have a ton of practice problems that are better practice than what's available in WebAssign. So you really, really need to do these problems in order to stay on top, because this will build so quickly. In order to stay on top of everything, tonight you should do the first 16 before tomorrow's lecture. So you should do 1 through 16 and not worry about the bottom of that, although you can look at 17 through 20 if you wanted. But tonight, I'm going to write it on the screen and then I'll share it again. Numbers 1 to 20 on the sequences 1 worksheet. You have the answers. I'm not collecting it, and so completely your call, but it'll become clear on the test whether you guys are really staying up on this or not. Just because it builds really fast, as you can tell already. I think it's building pretty quickly. So tonight we really need you to do these. That's more important than the WebAssign. The WebAssign, we're done with most of what's on this limits 1, but we're not quite done. We'll have some more of it tomorrow. And then sequences 2, we'll be working on that tomorrow, Thursday. And we'll talk tomorrow about a couple optional videos about prereq material that would be a good idea to look at if you don't feel comfortable with background in sequence series, which I think a lot of us don't have, which is fair. But the book kind of assumes you have some background in this. And that's why I made videos on stuff that you are supposed to know from before. All right, but anyway, to stay on top of where we are right now, take home quiz due tonight, and you should do the worksheet 1 through 20. Use the solutions to help you through it before tomorrow's lecture, and then just kind of between now and next Monday, be working on these. The second one's not up yet. All right, that is it for today, you guys. Thanks for coming. If you have questions, I have just a couple minutes, so stick around if you have a quick question. If not, I will see you guys tomorrow. Thanks, guys.